Welcome back to this series of seminars on the essentials of tensor calculus. Let's begin part 3 with a quick review of what we saw in parts 1 and 2. Recalling that these two parts comprise the first third of our agenda, namely a look at what well may have been seen in a multivariate calculus course. If you recall, mapping. This mapping takes you from the present coordinate system to a new coordinate system. We call that phi. Its inverse takes you from the new coordinate system back to the present coordinate system. We call that phi inverse. Each of these mappings has a Jacobian matrix. This is the notation for the two Jacobian matrices. These are partial derivatives. The upper index here is row. This lower index is column. These two matrices are matrix inverses. That's what this statement says. The columns of this Jacobian are tangent vectors, and we call them natural because we don't normalize them. The rows of this Jacobian matrix are natural gradient vectors, so normal vectors, normal to coordinate surfaces. Then we looked at transformation of coordinates. If you have a general tangent vector, which is a linear combination of tangent basis vectors, notice how upper, lower indices by the Einstein convention are summed. Well, the transformation law is the covariant transformation law. This is a Jacobian matrix. It is this Jacobian matrix. And my mnemonic for remembering this is put the Jacobian matrix to the left of the vector components. The sum from the perspective of the Jacobian matrix is upwards. So it's uphill. It's against gravity. Contravariant. If you have a general gradient vector, so these are the basis of gradient vectors. So you use a lower index on the component. Put the Jacobian matrix to the right of the vector. The sum from the perspective of the Jacobian matrix is downhill with gravity, co-gravity, covariant. And this is the Jacobian matrix for this transformation. This is the Jacobian matrix for that transformation. Having examined these preliminaries, these foundation points that we want to build our understanding of the concepts and notation of the tensor calculus on, let's now look at some issues in just tensor algebra, beginning with what is a tensor. So there's a thing called a tangent space, which is the collection of tangent vectors at a point P in a manifold. So all of these tangent vectors form the tangent space. There's a normal space, all of the normal vectors, all the gradient vectors at a point in the manifold. Then there is the notion of the tensor product of spaces, where you could take a tangent space with a tangent space with a normal space, or a normal space with a normal space. So think about that. You have two vector spaces, V and W. And the tensor product of these is typically denoted with this circle with the big X in it. It's a bigger vector space whose elements are all possible products, the members of one space with the members of another. And I like the dyadic basis understanding of what a tensor space looks like. So suppose a V has a basis AB. And W has a basis uppercase AB. A basis for the tensor product of E and W would be the set of dyads AA, AB, BA, BB. Whatever these objects are, they're some kind of basis objects. And then you take linear combination of those basis objects. In this instance, that linear combination would be a rank 2 tensor. It's a multilinear object defined on the tensor product of these two vector spaces. The coefficients, here I've used Z1, Z2, Z3, and Z4. These coefficients could be functions, typically well-behaved functions, because you want to take derivatives, so you want them to be in some sense smooth or differentiable or whatever. Okay, those coefficients are the components of the object called a tensor. So suppose you have a tangent space with the basis of tangent vectors, and you take the tensor product of TP with itself. So a rank 2 tensor defined on this tensor product would be an object of the form T11, this is the dyad E1E1, here's the dyad E1E2 with a coefficient T12. Here is the dyad E2E1, coefficient T21, and the dyad E22, coefficient T22. Notice if you use tangent vectors as basis in the vector space, then the coefficient has an upper index, just like for vectors. Suppose you had a normal space. So the basis for this two-dimensional normal space, E upper 1, E upper 2, you take a tensor product of NP with itself. The multilinear object defined on that tensor product would look like this, T with lower indices. And you have the same pattern for the dyads, and you have the same pattern for the coefficients. Now you could even have a tensor product between a tangent space and a normal space. So the dyads would have one lower index and one upper index. The coefficients of these basis elements would have correspondingly an upper index and a lower index. Okay? Upper, lower. Now the period will often be used to indicate that this is the space below that first index, and the second index, this lower index, has been shifted over one little space, typographical space, to indicate where this one sits. Now, the upper and lower indices correspond to the upper and lower indices on vectors, and transformations in the underlying spaces generate either the contravariant transformation law or the covariant transformation law, which manages what happens to the basis vectors, and therefore the coefficients inherit that change. And so the transformation laws, contravariant and covariant, are going to involve the Jacobian matrices. So let's use a notation here for the Jacobian matrices. And let's take a look at what happens to a tensor. It's the coefficients that we are looking at here. What happens to the coefficients? All right, so this is the set of coefficients in a present coordinate system. and we want to change coordinates and what's going to happen to the coefficients in the new coordinate system. Same thing that you saw for vectors. Two upper indices. Basis vectors are tangent basis vectors. And so the transformation law is the covariant transformation law. One for each index. And so this I is summed. And this J is summed. That results in the new coefficient in the new coordinate system. If the tensor is completely covariant, then it will have lower indices and it will be transformed according to the covariant transformation law. And you'll notice that we didn't change the position of the item with respect to the Jacobian matrix because we're just looking at sums. We're not thinking in terms of matrix products, we're just thinking in terms of sums. Now you want to convert that to matrix products in order to implement the computation that we find. And so there's a sum on the I here and the sum on the J here. And if it's mixed, you're going to have one Jacobian matrix and the other Jacobian matrix. So each index indicates which transformation law, which Jacobian matrix is going to have to be used. One of the first tensors that you might run across, and one of the most important ones, is this thing called the metric tensor. So what is the metric tensor? Let's see what this metric tensor is. Well, it's the collection of coefficients that you would get when you take dot products of basis vectors. These are the elements or entries or components of the metric tensor, and since it's a rank 2 tensor, it's easy to represent it with a matrix. But don't think of it as only a matrix. It's this collection of coefficients. And what are the coefficients? Well, here for the case n equals 2, you can see it's e1.e1, e1.e2, e2.e1. So these things are going to give you the same answer. So you have symmetry here. And e2.e2. Let's think a little bit further. Think of e1 as a row vector, here as a column vector. What would this tangent vector look like if it were transposed to be a row vector? Remember, it's derivative with respect to the new independent variable, and so going across the row, the derivatives will be the same. In the Jacobian matrix, that is as a column. So right here, it's the Jacobian matrix of the inverse transformation, but as a transpose because I want to make those row vectors. And so this product against this vector, we can represent this as the Jacobian matrix, the inverse transformation. There is the metric tensor with upper indices, and you get that with dot products of the gradient basis vectors. e1.e1, e1.e2, e2.e1, e2.e2. So again, think in terms of this is a row vector. Here we write it as a column vector. What would that row vector be? It would be gradient vector. either row. This matrix, as it's written, is J phi, the Jacobi matrix of the forward transformation. And then this is going to be the transpose. So here are two alternate ways to compute the coefficients, components of the metric tensor, this thing called Gij lower and Gij upper. Now clearly we want to make some connection between Gij with lower indices and Gij with upper indices, and in reality, if you think of these as matrices, they're inverse matrices. If you think of as just a collection of coefficients, then this product summed here on the second index and here on the first index, that's why it's easy to represent this as a product of two matrices, is the Kronecker delta. So they're inverse matrices. So this is the statement. The matrix representation of these two tensors are matrix inverses. Okay, so how would we verify that? Well, we have this representation of Gij lower and this representation of Gij upper, and so let's put it all together. Now, this product inside these two inner matrices, if multiplied together, is the product of two matrices that we know are inverses. And so I write I to replace that pair. So you can take it out. And now you have this transpose times that transpose. So put the transpose on the outside and switch the order of the matrices, and you have two matrices which are again known to be inverses of each other. So I've written I transpose equals I. So the metric tensor, if it's defined with lower indices, and here it's defined with upper indices as matrices, these two matrices are inverses of each other. So we've defined this tensor, Gij, and call it a metric tensor. Why do we use the word metric? It suggests we are measuring a length. So let's investigate how you might get the length of a tangent vector. So here is a tangent vector. It's a linear combination of two basis vectors that are tangent vectors. And I'm just going to do this in the case n equals 2. And how would you get the length of that? Well, the length squared is v dot v. So let's compute v dot v. Here's v, here's v. So you're going to have four terms. V upper, the coefficient, v upper 1. It's going to appear twice, one here and one here. E1 dot E1. There's your E1 dot E1. V1 E1, V2 E2. So there's your V1, there's your V2. E1 dot E2. Then V2 E2 times V1 E1. So there is your V2, there is your V1. You need E2 dot E1, there's E2 dot E1. And finally, this term times this term, V2, V2, E2 dot E2. Let's represent this as a bilinear form. If we put V1, V2 as a row vector and V1, V2 as a column vector, and look at this collection of coefficients, E1 dot E1, E1 dot E2, E2 dot E1, E2 dot E2, these numbers are the elements of the metric tensor. So you have a bilinear form, metric tensor, and you sum, and these sums represent this matrix product. That's the length squared of a vector. The vector has components VI, the upper I. So, metric tensor. This is the machine that helps you measure the length of tangent vectors. And it should be no surprise that if you do the same thing for a gradient vector, again in case n equals 2, so here is a gradient vector, a general vector which is a linear combination of the two gradient basis vectors. Take its length squared, v dot v. And so you are taking the dot product of these two vectors. And the pattern is exactly the same. You're going to v1 here and v1 here on the outside, e1 dot e1 between them. Then v1, v2, e1, e2. Pattern is exactly the same. And then v2, e2, and v1, e1, and v2, e2 with itself. v2 is on the outside, e2 dot e2 on the inside. You rewrite this as a bilinear form. Row vector here, column vector here. These dot products as a matrix. These are the elements of G upper ij. And so G upper ij is the matrix that you would use in the bilinear form that computes the length of a gradient vector. Again, the Gij, upper or lower, is called metric tensor because it arises naturally as the machine that allows you to measure the length of vectors. So how about an example, simple example? Let's use polar coordinates to look at a simple example of this idea of the metric tensor. So in polar coordinates, we need basis vectors. So here's the position vector. You take derivatives with respect to the independent variables, r and theta. This is a tangent vector. This is a tangent vector. Natural basis of tangent vectors. Then we have to take dot products. E1 dot E1, E1 dot E2, E2 dot E1. These are going to be the same by symmetry, and E2 dot E2. So here are the vectors. Cos times cos, sine times sine, cos squared, sine squared, 1. Here you have cos sine with an r, cos sine with an r. This has a minus sign. It's going to add up to 0. So if this adds to 0, this adds to 0. And finally down here, an r with an r is an r squared. The minus is minus times a minus is a plus. R times an r squared. Sine times sine, cos times cos. Sine squared plus cosine squared, that's 1. You get r squared. So the elements, or the entries of the metric tensor, if displayed as an array here, 1, 0, 0, r squared. Now I'd like to show how this result can be computed in Maple using, for example, the physics package. Okay, so install the physics package. And this is the preliminary stuff that it takes. You're telling the physics package the dimension is 2. The existing coordinates are x and y. And the metric, therefore, would be Euclidean. And this quiet suppresses a lot of output that just we don't have to look at the moment. And what happens is you transform coordinates. These are the equations for polar transform to polar coordinates, but this is the phi inverse. This is you're pulling back from polar to x and y. And you were telling Maple you want this metric tensor. These are the independent variables, and to set that metric and don't display a whole bunch of stuff. To ask for the metric tensor or the coefficients or a display of the metric tensor, you use this notation, G underscore with empty square brackets. And Maple responds with G lower, which is what we computed in our example, 100 r squared. If you want Gij upper, in this square brackets, you put a tilde. That's what the physics package uses to represent upper indices. And now you see as the response or the display, G mu nu upper. And this 1 over r squared is clearly the element of the inverse matrix if you are inverting this matrix. And so you can do these calculations in, for example, the physics package in a notation that does not look extremely difficult. So after using the metric tensor as the vehicle for calculating the length of vectors, the next thing that you see for the metric tensor is that it's involved in raising and lowering indices. Let's just look at this usage. We have a vector, and we give it in both its contravariant form and its covariant form. Okay, so contravariant form, the basis is the basis of tangent vectors. In its covariant form, the basis is the basis of gradient vectors. And what we are claiming is if you have a vector in contravariant form, see the upper index here, and you sum or multiply by the metric tensor, essentially a sum, J, the resulting coefficient is the covariant coefficient, and vice versa. If you have the covariant coefficient and you multiply and sum J here, with the metric tensor, G upper ij, you will get the coefficient of the contravariant form. And essentially, you have taken an upper index and lowered it, and here you have taken a lower index and raised it. This is the phenomena or the issue of raising and lowering indices. So first of all, you got to get clear. All raising and lowering indices means is you have changed the basis for representing the vector from tangent vectors to gradient vectors or from gradient vectors to tangent vectors. That's what raising and lowering indices is all about. It's a change of basis representation. And the next part that you want to look at is why does the metric tensor do that? So to understand why the metric tensor is the agent of changing bases, let's just take a look at some fundamental linear algebra for changing coordinates in linear algebra. And I'm going to look at the case n equals 2 for simplicity. And here we have a vector v described in two different bases. Basis vectors, little a, c, b, d coefficients. Can represent this as a matrix, a, b, c, d, times this vector, and I will call this matrix P. Suppose we have a different basis, A, C, B, D, uppercase letters, different coefficients. And I represent the differences here, lower indices, here, upper indices. So I have a matrix, A, B, C, D, vector. I'll call this matrix Q. Now, these two items have to be equal because it's the same vector. Therefore, if you want to know the upper in terms of the lower, you would multiply Q inverse against P and the vector. If you want to know the lower in terms of the upper, then you want to multiply P inverse against Q. So if you define this as the transition matrix T, then this transition matrix is T inverse. So it's useful to recollect that you have seen this idea of the transition matrix way back in linear algebra. So now let's apply this to our tangent and gradient vectors in the flow of ideas for tensor calculus. So we want to express V, a vector, with a tangent basis. Is a vector, V upper 1, V upper 2, E1, E2. We're using n equals 2 for simplicity. We've made a representation like this before. What is E1? It's a derivative of the position vector with respect to the new variable U1 here, and here it's with respect to U2. So this vector is dx du1, dx2 du1. Right, this is the first column of a Jacobian matrix. This is the second column of the Jacobian matrix. And so if you want to represent this sum compactly, you could take the Jacobian matrix of the inverse transformation. This would be J phi, because these are the columns, J phi, and multiply by V1, V2. You're taking a linear combination of those columns, and so this would then be a representation of the vector V. Now let's do exactly the same thing with gradient basis. So that vector V could also be represented V lower times E upper, right? E1, E2. These are normal gradient vectors. So I've written here that this is a gradient, and this vector is a gradient, and I'm reminding you what the gradient vectors look like. The derivatives, as you go across, change. It's dx1 here and dx2 here, but the function stays the same here. So how could we represent this compactly? This vector, we take this and make a column vector out of it. Okay? And we take this and we make a column vector out of it. So if we want to use the notation of a Jacobian, we have to recognize that this is the transpose of a Jacobian, because in a Jacobian, down the column, it's the same derivative. So this is J phi, Jacobian of the forward transformation, but it's transposed if you want to make this representation. So we now want to equate both versions of this vector V. One version, J phi inverse, V1, V2, where the indices are upper, J phi transpose, where the vector V has components with lower indices. So if you want to go from contravariant to covariant, you are doing this calculation. We'll isolate the lower indices and solve in terms of the upper indices. And so these are the contravariant coefficients, and I want to end up with the covariant coefficients. And so you can see what you have to do here. If you're multiplying, manipulating matrices, you have this matrix to invert and multiply against this matrix from the left. So we want to study this product. I'm going to interchange transpose and inverse. Then this inverse matrix is the Jacobian matrix of the inverse transformation. So what does this product now look like? Well, you have a transpose. Well, in that matrix you're going to transpose, you have column vectors, E1, E2. And here you have E1, E2. So here they're transposed. So now what does it look like? E1 is a row vector, multiplies this column vector, and so you have these dot products. E1.E1, E1.E2, E2.E1, E2.E2, but these numbers are exactly the numbers that you find in the metric tensor Gij, where you have lower indices. And so to go from contravariant to covariant, what appears? The metric tensor. Suppose we were to solve this so that we are going from covariant to contravariant. Well, these are the covariant coefficients. We want to end up with the contravariant coefficients. So we want to solve for these guys. So we have to invert this matrix and multiply from the left. So we take that matrix, invert it, and multiply from the left. Well, the inverse of J phi inverse is J phi. And this is J phi transpose. So let's look at what that's like. In J phi, the basis vectors are row vectors because they're gradients. And the transpose puts them as column vectors. And so now you start taking dot products, E1, E1, E2, E1, E2, E2, E1, E2, E2. These are the numbers you find in Gij upper. So again, the metric tensor becomes the transition matrix for changing basis. And changing basis amounts to raising and lowering indices. And so that's why the metric tensor is the machine that raises and lowers indices, because raising and lowering indices is nothing more than changing from tangent to gradient or gradient to tangent basis vectors. And now let's use an example to illustrate these two notions. V lower comes about by lowering the index on V upper, and it takes the metric tensor to do that, and you raise the index on V lower by multiplying, or it's really a summation of products using Gij or GKJ where it's upper. So let's do an example. And I would like to make this example be interesting, different, unusual. So I'm going to define a skew coordinate system. So the equations that I started out with were x is 2u, 3v, y is 5u minus 7v. So x is a function of u, where u has two coordinate names, u and little u, or script u and script v. That's phi inverse. So it's easy enough. These are linear equations you can invert. So the forward transformation, where you plug in x's and you get back u and v, are just solve. You could use the solve command, or you can use Cramer's rule and solve that way. This is what phi looks like. So then here's where a little bit of maple is useful. We've seen how we can use the physics package to obtain a metric tensor. And I've shunted that computation off to this worksheet, and it runs like it ran a bit earlier. But in the physics package, this is the setup command. It basically sets up Euclidean space, and then you transform and you pull back and you get the metric tensor in the new system. Here's what it looks like. I've written it here in a simplified form. You notice you can factor out 29, and here's a representation of G lower ij. To see what G upper ij looks like, you put the tilde in here, and you see these 1 over 29s. So if you pull out the 1 over 29, it's 2111. And since we're using this example to set ideas, let's get the metric tensor via its definition. So we'll write the tangent basis vectors. So you take the position vector, you differentiate with respect to u, you differentiate with respect to v, you get these two vectors as basis vectors, and then you have to do a bunch of dot products. So I've arranged those dot products, e1.e1, e1.e2, e2.e1, e2.e2. I've arranged them here in this tableau so you can actually follow with your eye some of these calculations. So here you have the dot product. You're going to get 4 and 25. There's your 29. Here you're going to get 6, negative 35. So there's your negative 29. This will be symmetric. And here it's 9 and 49. It's 58. And you can factor out 29 and you get the result we had earlier. Gradient basis vectors. Let's take gradients of these expressions here. You're going to get this vector 7i plus 3j over 29. You can see that. 7 and 3 and the division by 29. And here you have 5, negative 2 divided by 29. Okay, so when you take these dot products, you're going to have 1 over 29 from here and 1 over 29 from here. So I've written 1 over 29 squared, and I've just put the vectors in as column vectors so you can, so that your eye can follow the dot products. See, 7, 3 with itself, and here it's 7, 3 with 5, negative 2. Just do some of these calculations. 49 plus 9, you have a 58. Here it's 35 less 6, you have a 29. This is symmetric. 25 and 4 is 29. If you factor out 29, then 1 over the 29 squared you got one cancellation there. You got 1 over 29, 2, 1, 1, 1. So while we're at it, let's get the metric tensor as a transition matrix via product of Jacobians. So we need the Jacobian of phi inverse. So the columns have the same derivative. First column has derivative with respect to u. Second column has derivative with respect to v. 2, 5, 3, negative 7. And so think of those as column vectors. Tangents. J phi, gradient vectors. So we know what the gradient vectors are. We've seen them right here. So there's a 1 over 29, and you have 7, 3 goes across. 5, negative 2 goes across. Think of these as row vectors. So we saw that G, ij lower, is a product of Jacobian matrices of this distribution. So you take this matrix, it needs to be transposed. So notice 2, 5 becomes a row vector, 2, 5. And then you need J phi inverse, which is this matrix. So it's this guy not transposed. You multiply that together. 2 times 2 is 4. 5 times 5 gives you 29. First row. Second column, you're going to get a 6. And a negative 35 gives you negative 29, etc. Factor out the 29, and you have 1 minus 1 minus 1, 2. If you take this product of Jacobian matrices, you'll get G upper ij. So J phi is this matrix, and its transpose will also have a 1 over 29. So you get 1 over 29 squared, and you are taking this matrix, 7, 3, 5, negative 2, and you're multiplying by its transpose, 7, 5, 3, negative 2. Let's just take a quick look here. 7 times 7 is 49, and 9 is 58. 7, 5 is 35. Take away 6 is 29. Factor out the common 29. Instead of having 1 over 29 squared, you have 1 over 29, and you get 2, 1, 1, 1, as we got before. So all of these various ways of getting the metric tensor for some coordinate system can be verified in these simple cases. The arithmetic is not too bad, and if the arithmetic is bad, you always have Maple do it for you. So this concludes part 3, a look at the algebraic manipulations associated with a tensor. As heavily involved looking at the metric tensor and explained why that metric tensor appears in the operations of raising and lowering indices. The remaining 2 webinars in this series will explore the tensor calculus itself. And material for parts 1 through 3 will be made available to anyone who contacts me by email and asks for them. My email address is rlopez@maplesoft.com. rlopez@maplesoft.com. If you already have the materials for the earlier parts, when you get the new batch of files, you can just simply discard the previous ones, because then you'll have parts 1 through 3.